Okay. Sorry, the slide berapa ni? Tak ingat lah. Baru nak rakam. Number 5. Okay, second law of thermodynamics. Second law of thermodynamics. So okay, the definition of second law. It says define that energy has quality as well as quantity. An actual process occur in the direction of decreasing quality of energy. Faham tak? Okay, okay, it's a bit complicated, the definition, but it's like this. Okay, simple definition first. So actually, if we only apply, if we only have the first law just now, energy, means that we calculate how much the energy that this our body can produce, how much the energy that the gas turbine engine, the power plant can produce, etc. But it's actually the not all of the energy produced is being really used. Okay, maybe like we produce 100 joule of energy, 100 joule, but not all of this 100 joule is going to be well used. Okay, will be transformed into work. Okay, will be used. Okay, by the human or by the machine or etc. So the actual percentage or the actual parts of the energy, amount of energy, quantity of energy that being used, maybe like 70 joule, only 70 or 50%, right? So that is what the second law of thermodynamics mean. Okay, so the second law of thermodynamics, it measure the actual process, the actual quantity of the energy being used or being that can be used. Because sometimes we produce 100 joule, but part of it is like a waste energy. It cannot be used. Maybe the energy is a low grade energy. Means maybe the temperature is not very high. Okay, so it's like a waste energy. So only the amount of actual energy that we can actually be used, that is accounted by second law of thermodynamics. Okay, general view first. Okay, kalau later on in chapter 6 which is 7, we will learn we will look into detail about the second law of thermodynamics, but I'm just going to tell you the general definition. So the difference between first law and second law. First law, you measure the whole energy, amount of energy. Second law, we are going to quantify, to calculate, to measure the actual energy being used, or the actual useful energy, we call it, the quality of the energy. Like you produce 100 joule, but maybe not all this 100 joule is going to be used, or is, we call, other quality, has quality. Okay, so and another thing, this second law of thermodynamics is also related to the irreversible process. Reverse, constant, reverse, and irreversible, cannot be reversed. Okay, so it's like what do you mean by that? Is that reversible and irreversible process? For example, this hot coffee, right? Okay, this hot coffee, coffee ni kan. Okay, this hot coffee, this hot coffee at 70 degrees, and the environment, the ambient temperature, the room temperature is 20 degree. So normally, secara fitrahnya, when you put a cup of hot coffee in the room temperature, even though you didn't plug in anything, any electricity or anything, the hot coffee will be the heat from the hot coffee will be transferred to the environment. So, and then it will be cooled down slowly, right? So the heat will be transferred. Okay, this red heat will be transferred from the hot fluid to cool environment, cold fluid. But can we reverse back the process? Means that can the energy, the temperature the heat from the cool environment can be transferred back to the hot coffee? Can we reverse back? The answer is no. Okay, if you don't put any electricity or any refrigerator, right, here, so naturally it will not be the process will not be reversed back. It can't be it is irreversible. It can't be reversed. Okay, from the cold back to the hot, right? Kalau kita tak put, we don't put any electricity or anything, and okay, so that is irreversible process. Okay. Now, that what it means by irreversible process. So a lot of phenomena process in this world is irreversible. Actually, you cannot what move back, patah balik, kan, like macam sekarang, like now you cannot move back to your younger self, right? Okay. Another thing, handphone. If you drop your handphone, okay, pecah, it broke down, then you cannot reverse back. Okay, the handphone, even though you pick it up back, but the phone is already broken. So it's not irreversible. It is not reversible. It is irreversible. Okay, classical thermodynamics and macroscopic approach. Macroscopic approach. Okay. To the study of thermodynamics that does not require a knowledge of the behavior of individual particles. Okay. Okay, there is two method, okay, to approach to understand the thermodynamics process. One is macroscopic and another one is micro. Okay, so when we want to solve thermodynamic problems, firstly we have to identify first what is your system, the closed system. For example, like again, this hot coffee, right? Our system, the system that we are going to consider is the cup, the hot coffee, the mug, and the cool environment. The means that the environment only at the surrounding, okay, environment at the surrounding, not on the, maybe the room is like 20 meters square, but you only, the system that you're going to consider only this maybe 2 times 2, 4 meters square, 4 meters square, right? Even though the room is big, but the system that you're going to study, to concentrate, to analyze is only this system. Okay, so when you want to solve thermodynamic problems, first you have to state first what is your system. Okay, first, so in your exam or in your test or in future, right, you state first the system, the closed system that we are going to consider is hot coffee and the surrounding environment near to the hot coffee, maybe around how much the area, right? You precise the area. So we only consider that. So means that if we do macroscopic approach, means that we study the heat transfer process, the thermodynamic process only in this closed system. So we only focus in this all the behavior process, particles or anything change the movement in this specific system. Okay. Okay. Apa tu nanti we learn more, okay, about this. This one figure 1 tu apa ni? Conservation of energy principle for the human body. This is even us, human body also, we have we transform energy. Means that we eat a lot. For example, we eat our breakfast and then we use that the energy from the breakfast that we ate, nasi lemak, roti canai. So the calorie, right? The calorie is being burned and we use that calorie for our energy, okay, to study or to exercise or to do anything, right? So the energy is being transformed from the chemical process of the thing that we ate, the food that we ate, to the physical, yeah, to our physical, okay, the energy of human body. Okay, next, okay, this is some application area of thermodynamic. Okay. Maybe nanti kita we take another rest at 10:30 macam tu Okay. Nanti 5. Okay. Application areas of thermodynamics. Okay. So this is example. Okay. First, figure 1.4. Okay. House. Okay. Residential building. Like I mentioned just now, if you want to be, if you want one day you want to work in the renewable energy or sustainable energy area, you want to design something, maybe some of you will not work in the aircraft area, aerospace area, and you want to but you want to work in the renewable energy or sustainable energy area with TMB or anything, right? Okay, means that you can, because you have learned this, you have learned thermodynamics, one part of it, right? So you can work in that area also. So what does this thermodynamics do? Okay, for example, we design, okay, many engineering systems such as the solar hot water system involves thermodynamics. So in order for you to design a house, a residential building with renewable energy or sustainable energy, energy efficient system, okay, you want to include solar hot water in your house, shower, right? Solar photovoltaic panel at the rooftop, yes, to use solar PV, more clean energy, right? So you need to understand thermodynamics first, okay? So for you, in order for you to design, because you are going to calculate how much is the energy efficiency, how much is the performance, is this worth it or not, okay? To apply this concept in a house, a big house or a small house, it depends, okay? How much the heat is being exchanged, being transferred, okay? So the pump, heat exchanger, etc. That is, all of this is the fundamental of thermodynamics, okay? And then refrigerator, okay? Refrigerator also, how going to store your food in your refrigerator. So you need to understand the process of the refrigerator, right? So for maybe you want to set a certain temperature. So you want to design a refrigerator that can contain food at a certain level of temperature for how long, right? More efficient, etc. So you need to understand the energy process behind. Okay, in order to how much the energy, for example, of how much the heat transfer from the condenser in the refrigerator to the food, the temperature, energy, etc. So in order to achieve that energy, how much time it takes, right? So for you to design that, you need to understand the process. Okay, and boats also, the mechanical movement is the same as any other vehicles. So how are you going to operate the boats? And then aircraft, of course, this is your main part. Okay, aircraft and spacecraft. We will learn about the application of thermodynamics in propulsion system of the aircraft. Okay, the engine here, ni engine, turbofan normally. Okay, in civil aircraft normally we use turbofan. Okay, and power plants. Okay. Your the gas power cycles that I mentioned at the beginning, the gas power cycles can be applied in aircraft or power plants. Kilang-kilang, industrial power plant, right? You want a power plant, for example, has metal, right? Industry, right? So you need to understand the gas power cycles process. Gas power cycles. Okay. Because this gas power cycles is going to be applied in the power plant industry process. So sama je, same as aircraft. So these are some of the not all, some of the application of thermodynamics related to energy. Okay, ada lagi. Human body, like I mentioned just now, human body also kan. kita makan, whatever we eat, we use it as energy. Cars, same as wind turbines. Okay, wind turbines, another concept of renewable energy. Okay, solar just now is from the sun, the heat, the thermal energy from the sun is being transformed to heat and electrical power. Here, wind turbine, we use the wind energy. So if the wind is strong, okay, but normally in Malaysia tak banyak sangat sebab our climate, wind and our wind speed is not really very very strong for us in Malaysia to use wind turbine, wind energy. So wind turbine transform the wind energy, okay, the wind power to electricity, to power, okay, by using turbines. So the turbines is the device that transform the process from the wind energy to electrical power or mechanical power. Okay. Food processing, okay, to process the food, kilang-kilang, just now, okay, a piping network in an industrial facility, okay, piping, also to understand the piping, to design the piping process, kan, how much the pressure in the pipe, so this one related also with fluid mechanics, okay, the Bernoulli principle, so you apply the Bernoulli principle, fluid mechanics plus the thermodynamics, so you know you can design a piping network. So means that in the future, it doesn't mean that you have you can only work in aircraft, aerospace area. You can also work in all of this area. Okay, wind energy, piping, etc., hydraulic. Okay. So actually mechanical ni, because aerospace is part of the mechanical engineering area, one of the specific area in mechanical. So mechanical actually is very broad area. So don't worry, you can apply in a lot of application. Okay. Okay, next is dimension units. Okay, dimension units. This is a very simple one. Okay, any physical quantity can be characterized by dimensions. Okay, so so anything physical value we can measure. Okay, can be measured. The magnitudes of this dimension is called units. Okay, for example, temperature, the unit is Kelvin, degree Celsius. Distance, the dimension is distance, the unit is meter, kilometer, centimeter. Okay, so some basic dimensions. So the basic dimension that you already know, length, the mass, time, temperature, and then we are primary and secondary. Okay, secondary volume, energy. So this secondary dimension is being derived from the primary, the basic dimension. Okay, and then this is the unit that we use normally is SI units. English system is sometimes used like Fahrenheit, pound. Okay, but as we sometimes we have the mass in pounds, we have to convert to SI, which is kilogram. Okay. So you need to know for all of the, especially the basic dimensions, what is their SI units. For example, mass. The SI units for mass is what? Gram or kilogram? Baca. Gram or kilogram? Marwan. Marwan, I think you just enter. What is the SI units for mass?
Yes, doctor.
What is the SI units for mass?
Newton.
Newton?
Oh, sorry for force.
Unit, mass.
Kilograms.
Okay, kilogram. Okay, not gram. Okay, so that one, you have to be alert. Okay, all of you lah. Have to be, not gram, is kilogram, because when you calculate energy, or when you calculate force, Newton, is in kilogram meter second. It's not gram. Okay. And then length, meter, time, and time is the SI units is actually second, not minute, or hour. Okay. Ada lagi masuk. Okay. Okay, these are the units. Okay, pass. Okay, jap. So at least you know this one. Remember this one until giga or mega here. Okay, the one that we are going to mostly use. Centimeter, micro, maybe. Okay, all the units means that millimeter is how much? 10 power of minus 3 or minus 2. Okay, that one you have to remember. Some SI, so this example SI in English units. Okay, like I mentioned just now, the English unit is pound mass. So pound mass is equivalent to 0.45 kilogram, or 1 feet is in English. SI units is 0.3 meter. Okay, so this is force, mass, time, acceleration. So this one you know, work, force, and work is force times distance. So it is Newton meter, and the SI units is joule for work. SI units is joule, but if you change joule, it will be kilogram square, like this. Okay, because meter. So that's why you need to remember. If you don't remember joule, at least you know the definition that work is force times distance. So you know force is MA, or kilogram meter per second square, times distance, multiply with distance, meter. So we have this unit. This is joule. Energy or work. Okay. Okay, this one SI unit prefix I use. Okay, example. This our example. Okay. What else? Relative magnitude of the force. Okay, Newton, kilogram force. Okay, weight. Okay, this one you know. Weight or Newton. Weight is in Newton. So it's mass time the gravitational acceleration, mg. That's why we have potential energy. The weight of a unit volume of a substance. Okay, tak apa. Pass. Okay. Conversion ratio. Tak apa. Okay. Sorry, yeah. I pass means okay. You can just review. Okay, so this is an example of how you calculate the weight. Okay, you have the mass and change it into kilogram. That's why it is divided by 1000, because you need to change into SI units. Okay, this one. And multiply with the acceleration force. So we have 4.49 Newton. Okay. This one, system and control volume. Okay. System and control volume. So system, a quantity of matter or a region in space chosen for study. Okay. So okay, like the example of a hot coffee just now. Okay. Coffee and the surrounding just now. Okay. So we choose. This is the system that we choose. Okay. That we want to study. So a quantity of matter or a region in space chosen for study. So this is a system, a closed system that we use. Okay. But you need to remember apa ni? Okay. This one is closed system. But for closed system, control mass, a fixed amount of mass and no mass can cross its boundary. Okay. a system is a quantity of matter, a system, but there is two types of system, closed system and open system. Okay, close, open, open, close. Okay, so a closed system is where we consider that there is no thermal exchange or anything being exchanged out in and out of the system. Okay, so for example, this one, if we consider that this this area, the coffee and the surrounding area, not the whole room, just the surrounding area of the coffee, is our system that we're going to study to analyze. So and if we consider that it is a closed system, so means that we don't take into consideration the energy or the thermal exchange, the work exchange in or out of this system. You only consider inside here, not outside. Okay. But if but means that there is no mass or energy anything amount cross its boundary. But if it's an open system, for example, the aircraft engine, the cycle, the thermodynamic cycle, the gas power cycles of the aircraft engine is an open system. It is not closed, obviously, because you imagine the aircraft engine in the air, so it is open. Okay, so you still have to define the system of the engine aircraft, but when we say that it is open system, means that we have to take into consideration the change of mass, the change of fluid outside the boundary of the system. Okay, so for example, okay, you have the okay, I only draw the engine aircraft. Sorry, this is only the engine part, engine, the turbofan part of the aircraft. You know where is the turbofan part in the aircraft? Dekat wing ni kan, at the wing of the aircraft. I only have one picture of aircraft here. This one, right? So here is the turbofan engine, the engine, engine. Depends on how many there. Okay, only this engine. Okay, so engine. Oops. So, mana tadi? Oops. Okay, this one. So engine, turbofan engine. So okay, this is our system, the aircraft engine. But since it is an open system, so we need to consider the fluid, the transfer of mass at the boundary also. Means that if there is any change in the air surroundings, means that we have to take into consideration. Okay, the force that the force that is applied near the engine, so in and out, etc. So we have to take that into consideration if it's an open system. Okay. Okay, back to surrounding the mass origin outside the system. Boundary, the real or imaginary surface that separate the system from its surroundings. Okay, so this is the boundary. Means that the boundary is not a physical thing. We cannot see the boundary. Is us who define the boundary. We define the scientist, the engineer. We define the boundary that we want to study. The boundary is not it is not in real life. Actually, it is not real, but we define the boundary. So the boundary, the real or imaginary surface that separates the system from its surroundings. Okay. Or sometimes it can be real. For example, if your system is if my system is the whole bedroom, my room here. So this is like the size of the room, the area of the room is my real boundary. Yeah. Okay. Okay, so the real or imaginary surface, real or imaginary, and then the boundary of a system can be fixed or movable. Okay, but normally we use here in thermodynamics the fixed boundary, so it's easier for us to define. Movable is more complicated. Okay, a system may be considered closed. Okay, Okay, so this one. Ada pun gambar. So this one So this one, oops. So this one, okay, surrounding. So you imagine you have a system. So the system can be any shapes, okay, systems. So this is your system. So the outside here, the ambient is the surroundings, and the dotted red lines is your boundary, okay. Uh, okay, so, oops. Okay, so this is a closed system. Okay, mass cannot cross the boundaries of a closed system, but energy can. Okay, so for a closed system, with a constant mass, the mass mean here that the particle, any particles or any fluid cannot be cannot cross the boundary. Okay, you cannot if you have this closed system as your boundary, ni kan. Okay, so means that other particles or other fluid cannot simply go into here. Okay, so there is no mass transfer, but energy, yes, energy can change, okay, in the closed system. So that's why, like the cup coffee just now, even though the cup is like that, but it can change energy with the surroundings, okay. And then okay, this one fixed boundary, moving boundary, okay. So for example, if we below here, this one is fixed, the boundary at the bottom, but the upper at the upper level boundary, this one is move. For example, if we have a piston here, so the piston is moving. So the upper boundary is changing, depends on the movement of the piston. Okay. Apa lagi? Dah, sorry, is it 10? Okay, we take a break. I think we need to take a break a bit, maybe around 10 minutes. Okay, I give you a break to refresh a bit. Okay, maybe take some breakfast if you haven't. Okay, 10 minutes. Okay, so until 10:45. Boleh? 10:32 for 13 minutes. Okay, we break until 10:45. We resume back. Okay, okay semua rehat
Okey,
Okay.
doktor.
Okay, 10:45 kita datang balik Okay, saya stop dulu recording kejap.